Hello! In this video, we are going to derive the center of mass of a hemisphere. So as you can see, here we have a hemisphere with radius capital R. Now, it's pretty clear by symmetry that the center of mass of the hemisphere lies on the z-axis. Let's say about right here. So really, the x-coordinate of the center mass is 0, and the y-coordinate of the center mass is 0. So all that's left to be figured out is the z-coordinate of the center of mass. And to compute the z-coordinate of the center mass, we can use the following formula. The integral of z dm divided by the integral of dm, where dm refers to a differential mass of our hemisphere. Let's say, for instance, and z represents the z-coordinate of our differential mass. Now first, let's re-express dm in terms of density. If you recall, differential mass is equal to density times differential volume. So let's re-express dm as d dv. Now for our purposes, we're going to treat density as though it's constant. So we have uniform density throughout our sphere, which means we can pull d to the outside of our integrals. So density cancels out, and we're left with this. So at this point, it looks like we have two integrals we need to evaluate. But really, this bottom integral just refers to the total volume of our hemisphere. And the volume of a hemisphere is half the volume of a sphere. So, since the volume of a sphere is 4/3 pi r cubed, this means the volume of our hemisphere is 2/3 pi r cubed. And now, let me just get rid of this big fraction right here, so we can rewrite this as this. Now, at this point, all that's left to do is we need to evaluate this integral. And the technique we're going to use is we're going to convert this integral into spherical coordinates. The reason why is because, well, we're dealing with a spherical object. So spherical coordinates might be useful. Now, if you recall, the spherical coordinates are rho, phi, and theta, where rho refers to the distance from the origin to our differential mass. Phi refers to the angle from the positive z-axis to our differential mass. And theta refers to the angle from the positive x-axis counterclockwise to the projection of our differential mass onto the xy plane. So first, let's draw the projection of our differential mass onto the xy plane. To do that, what we do is we draw a dashed line from our differential mass to the xy plane. And let's say that this is the intersection of this dashed line with the xy plane. Well then, let's just draw a dashed line from the origin to this point. And really, we drew this dashed line so that it was perpendicular to the xy plane. So really, this point represents the projection of our differential mass onto the xy plane. And theta is this angle right here. Right? So these are our three spherical coordinates. So let's re-express our integral in terms of spherical coordinates. If we recall, in spherical coordinates, dv is equal to rho squared sine phi, d rho d phi d theta. And what is z in spherical coordinates? Well, we can use this right triangle to derive what it is, right? Z is equal to rho cosine phi. So now, let's rewrite this integral by substituting z for this and dv for this. Now, in doing so, we realize that we're evaluating a triple integral because we have three differentials. So this is ultimately the integral that we're going to be evaluating. So let's figure out what our bounds of integration are going to be. Well, let's remember this integral refers to d rho, this integral refers to d phi, and this integral refers to d theta. Let's first talk about our bounds of integration for our integral with d rho. Well, we are integrating from a distance of 0 from the origin to a distance of capital R from the origin. As for our integral with respect to phi, we are integrating from an angle of 0 radians from the positive z-axis to an angle of pi over 2 radians from the positive z-axis. And finally, as for our integral with respect to theta, we are integrating from an angle of 0 radians from the positive x-axis through a full 2 pi radians. Right, so these bounds of integration will cover our entire hemisphere. So this is what we're going to evaluate. And so let's move back up to the top. Now first, let's just re-express our integrand as rho cubed sine phi cosine phi. Now, a technique you can use when evaluating multiple integrals is you can sometimes re-express this as a product of separate integrals. And in this case, we can do that. Right? Really, this entire thing is just the integral from 0 to r of rho cubed d rho times the integral from 0 to pi over 2 of sine phi cosine phi d phi times the integral of 0 to 2 pi of d theta. I'll call this integral number 1, integral number 2, and integral number 3. And so now, let's evaluate these 3 integrals separately, starting with integral number 1. Now really, to evaluate this integral, all we got to do is use the reverse power rule, right? The integral of rho cubed is just 1/4 rho to the 4th, right? And our bounds go from 0 to r, so really, this is just going to be 1/4 r to the 4th minus 1/4 times 0 to the 4th, and that just gives us 1/4 r to the 4th. So this is the answer to integral number 1. Next, let's evaluate integral number 2. Now, to evaluate this integral, we can just use u substitution. We'll take u to be sine phi, and therefore du is cosine phi d phi. So as you can see, we're going to take sine phi to be u, and cosine phi d phi to be du. So really, our integral becomes the integral of u du. But remember, when we change variables, we have to think about what our bounds of integration become. Well, we can use the relationship between phi and u to determine that. We see when phi equals 0, u is equal to sine of 0, which is just 0. And when phi is equal to pi over 2, u is equal to sine of pi over 2, which is just 1. So this is our new integral. And the integral of u is just 1/2 u squared. And our bounds of integration go from 0 to 1. So really, this is just 1/2 times 1 squared minus 1/2 times 0 squared. And that just gives us 1/2. So this is the answer to integral number 2. And finally, let's evaluate integral number 3. Now, I think it's pretty clear that the answer to this integral is just equal to 2 pi. So, now that we have the answers to all 3 integrals, let's go back and substitute these 3 integrals for each of their values. And now let's see how this simplifies. We see that the pi's cancel out. We see that r to the 4th divided by r cubed is equal to r. So r cubed goes away, and I'll just rewrite that as just r. So we see that we have also the 2's cancel out. So we see 3/2 times 1/4 times r, and that's just equal to 3/8 r. So this is the z-coordinate of the center of mass. So we have the x-coordinate of the center of mass and the y-coordinate of the center of mass. So really, the center of mass of the hemisphere is at 0, 0, 3/8 r. So I guess 3/8 is the magic number, right? That was good. And so yeah, that's pretty much it for this video.